Yes, so our last talk of the day is from Benny Applebaum, and he will be talking to us about how to make a combiner for zero-knowledge proofs.
Okay, yeah, thanks. So thank you for organizing this nice workshop, and this is a joint work with my student, Liran Kahlon, who graduated recently, unfortunately. And that's a good opportunity to mention that we have a very nice crypto group in Tel-Aviv University, and we have some available poster positions. So if you're interested, let me know. So let me start with a riddle, because the title is too long to explain by itself. So let's say that you want to prove a theorem in class, and you don't want to give too much details. Actually, you want to prove the theorem in zero knowledge. And at your disposal, you have 3 TAs. But one of them is not sound, and one of them is not zero knowledge. He chats, right? I mean, too much with the students. But you don't know which is which, right? I mean, who is who. And the question is how you can use these TAs in order to prove the theorem in zero knowledge, right? So you can think about it during the talk. And let me say that more generally, this is a question about combining, right? I mean, combiners are very basic objects in cryptography. And think about having many components of zero knowledge proofs. Only majority of them are good in terms of soundness and zero knowledge, and you want to somehow combine them into a single system. And ideally, you want to do it in a black box way, a non-interactive way, and so on. And let me say that I didn't formally define the problem, but let me say that there are only partial solutions currently. So the existing solutions either do not scale up with the number of components, or have to assume that you have more than honest majority number of components, let's say 2/3 or something like a large constant larger than half. Question already, yes?
Only a majority of them are sound and Z3, or
like in the slide. The slide, the example gives you the solution, right? So, okay. So that's the first question. The second question is that, shouldn't this talk be like 3 weeks ago, right? I mean, this is about proofs. We are in on MPC. And I'll try to answer these 2 questions during the talk. I mean, so we'll see if I'll do it. So in this talk, we're going to talk about secret sharing for an NP statement. I think that this is a very interesting notion. And the way that I like to think about it as a cryptographic variant of standard NP reductions. And as we will see, the definition is somewhat subtle, so we're going to spend some time in order to define it properly, or the way that I think it's proper. And later we'll see that it's not only cool, it will allow us to solve several problems. It allows us to get many combiners for zero knowledge proofs in a very strong way, right? Very robust, very black box, etc. We'll use it to solve some open questions in zero knowledge MPC and MPC, and it turns out that this tool is exactly what you need in different scenarios, although in these different scenarios, when we looked at them in the beginning, we didn't realize that this is the missing tool. And finally, if time permits, I'm going to show you how to construct these things. And for this, we're going to use some weird notion of MPC, somewhat non-intuitive, but we'll talk about how to construct it maybe, if we'll have time. Yes?
So you were saying that you need a majority of the components to be...
At the previous slide, this is a necessary assumption. Think about it.
Because sometimes you just need one, right? For some objects.
If you don't know, for this kind of, if you formalize the question in the natural way, you'll see that without honest majority kind of assumption, this thing is impossible. So exercise to the audience. Good, so standard secret sharing, we have a piece data item, right, a bit, or maybe a field element, and we map it into, we have this randomized mapping, split it into many shares, such that if you have T of these shares, you can recover the secret, and if you have only T minus 1, you learn nothing about the secret, right? That's a classical notion, we all know, and I guess love it. And now I want to talk about what it means to share an NP statement. Okay? So this notion goes back to this beautiful work of Goyal et al. Although they use a different formulation than the one that I'm using, and this difference actually matters, but since I have only kind of 30 minutes, I'm not going to have time to talk about the differences. So let me start with a naive definition, and later we'll fix it and get what I think is the right definition. So again, I want to share not a data item, but a statement. So what do I have in my head? I have an NP statement, let's say circuit SAT, and a witness, okay, an assignment. And I want a deterministic instance mapping that takes this circuit sat instance and generates many instances, okay? And the mapping that takes this assignment and generates many witnesses, okay? And what do I know? So this is a randomized mapping, okay? We want some notion of privacy, and that's why we need randomness somewhere in this system. So what do I want these mappings to satisfy? So I want three properties. You see this is the analog properties of secret sharing. So first of all, correctness, this is kind of trivial. If X satisfies the original statement, then these Y's should satisfy all these F's. Okay, so yeah. Privacy means that if you get to see only few of these satisfying assignments, it gives you no information on the original assignment. And I want to define it in a very strong way, okay? So I want to assume that I have a simulator that takes only the instance, not the witness, and generate this distribution, right? I mean, this small number of assignments. And it will be very convenient for me to assume that this is kind of perfectly secure, okay? Not only for kind of aesthetics, but it's also going to be very useful in terms of both applications and in order to construct this object. Okay. Good. So that's privacy. Now recovery means that if for some reason I get to see, let's say t plus 1 or t, sorry, the threshold, t satisfying assignments for this thing, then it means that f can be satisfied. And again, I want to actually require something stronger. It means that I can decode efficiently a satisfying assignment. Okay, so this is kind of clear. This is very similar to the notion of secret sharing. What's the problem with this notion? Impossible, right? Who said it? Right. That's always the problem with when things are too elegant. So if you can construct it, you can prove that P is equal to NP. Maybe this is true, but this is beyond the current work. So let's see why. So I can, assuming that I have this thing, I can check whether f is satisfiable as follows. I'm going to run the simulator for each of these instances, get an assignment, check whether it satisfies the previous thing, right? If this is satisfiable, then the simulator should work, this thing should satisfy, and then use the recovery algorithm and recover a satisfying assignment. And I can even check that it satisfies f. So this is impossible to achieve, so we'll have to slightly change the definition. And the way that we're going to change it is to allow these circuit sat instances to depend on the same set of variables. So I have a global assignment now, and these guys look at different parts of this assignment, and there are some intersections. So these circuit sat instances are in a sense correlated. Okay?
But now it's just ZK-PCP.
We'll talk about it in a minute. I mean, I have a slide about this. I'm not sure that we'll have time, but I'll get back to this point. It's not. You can think about it in the same framework as zero-knowledge PCP, but you'll see that this is kind of stronger than zero-knowledge PCP in some aspects and weaker in some other aspects. That's a short answer. Okay.
It's exactly the same to me. So,
Let's wait and see the definition, and then, okay. But you're right that this is very similar, or conceptually similar. So now I have this intersection, and again, I want to require the previous properties. So if this is satisfying, that this is satisfying. I have a simulator that given f generates, let's say, a satisfying assignment that satisfies any, say, two of these statements. And I have a decoder that takes something that satisfies at least three of these instances and generates a satisfying assignment. Okay? And now the previous kind of attack does not work, because when I run the simulator on different, say, pairs, it's not clear how to glue these partial assignments together, right? They have to be consistent with respect to a single global assignment. Okay, so at least we cannot rule this out. Unfortunately, I'm not sure whether this thing is realizable. Right? I cannot rule it out, but I don't know how to construct it. In order to construct something, I'll have to slightly relax this definition. I'm going to do the following thing. So the first step is just for convenience. Instead of talking about a single global assignment, I'm going to think about many different assignments that are kind of partial assignments. They have to agree on the same variables when the variables are assigned, but they can unassign some variables. Okay, so this is just a notational maneuver, right? They didn't change anything. Now, when I look at this partial assignment that satisfies F1, it's very clear that if a variable does not affect F1, I can keep it unassigned. But what I'm going to allow is something stronger. Even if this variable affects F1, I'm going to allow it to remain unassigned. Okay? And this sounds a bit weird at the beginning, but you'll see where it comes from, hopefully, towards the end of the talk. But right now, I have to kind of define how the logic works over unassigned variables, right? I mean, and the way that I do it is the natural way. So if I have an OR gate of 1 and unassigned variable, the outcome is 1, right? And if I have AND and 0 and unassigned variable, the output is 0. And otherwise, when you apply some logical operation over unassigned variable, the output is unassigned, okay? And when I say that the circuit is satisfiable, I mean that the circuit evaluates to 1. So if the output is unassigned, this thing is not satisfied. Good. So this is the definition, and how am I doing with the time? Let's see two kind of naive attempts that don't work, just to make sure that we understand this notion. So one thing, kind of naive thing to do is just to copy the assignment and duplicate this function. So it's not hard to see that this kind of satisfy correctness and recovery, but there's no privacy here, right? I mean, if I give you just one assignment that satisfies just F, you learn everything. Right? So this is kind of 1 out of n if you want, right? Because the privacy is kind of a trivial 40 minus 1. Let's try another attempt. Let's just secreture the assignment. Okay, let's do Shamir secretoring for the assignment. Now it's not completely clear how to define these FIs. And if you think about it more than 2 seconds, you see that this is actually impossible. So you cannot define the FIs in a meaningful way unless P is not equal to NP, for the same reason as that we had before. Right? I mean, there is no way that these things do not overlap. And therefore, you can show that this is impossible to achieve. Again, think about it a few minutes and you'll see why. Good. So NPSS versus zero-knowledge PCPs. Let's keep this thing for the end because I have more important thing to say. But let me say that you can think about these two objects in the same framework. The thing with so this is for the people who are aware of, who are familiar with zero-knowledge PCPs. Other people can kind of, it's not super important, this comment. The thing with NPSS that I insist on this sharp threshold, right? And typically in zero-knowledge PCP, you don't insist on the sharp threshold. On the other hand, zero-knowledge PCP typically should handle malicious verifier and so on. And here, this is kind of an honest kind of a creature. So that's, and I can elaborate later if you want. Okay, so it's a nice slide, but we don't have time for it. Okay, so the main result is a construction of T out of n NPSS for arbitrary T and n. Again, this is information theoretic construction, so we have perfect correctness, perfect privacy, perfect recovery. The running time is polynomial in n in the size of the instance. And I mentioned that some variant of this notion existed before, so let me tell you what was known before. So previously, they had, Goyal et al. Had some computational variant of NPSS. They were able to construct n out of n NPSS, and an NPSS where you have a big gap between the privacy and the correctness threshold. So that was the previous result. In the paper, they write public encryption and all sorts of things. As far as I can see, they just need one-way functions, but I don't know, read the paper and yeah, I don't see why they need more than this. I mean, they use it in other things and they don't really separate the object from its application, so the assumptions are a bit mixed up. But as far as I can see, they actually need one-way functions. Okay, so I said that we're going to construct it based on a new notion of MPC. Let me postpone this part and focus on the applications. So we're going to see in a minute how this thing can be used to combine zero-knowledge proofs. Maybe some of you already see it. So we're going to have all sorts of applications in this domain, but one thing that maybe is more interesting for people in the audience, in this audience, is that we get a general MPC protocol in the following settings. So you have honest majority. You want active security with guaranteed output delivery. You want 3 rounds, which is optimal. We know that you cannot go below 3 rounds. And all you need is one-way function. And we know that this is necessary. We know that this cannot be achieved information theoretically. So this is a result. So this notion without the one-way function was something that quite a few people worked on. And if we compare it to the previous Simon's workshop, Like 10 years ago, we knew how to construct it based on threshold fully homomorphic encryption plus CRS plus NISC. This is kind of, I think, a rare example where in 1 decade we went from FHE or even threshold FHE all the way down to one-way functions.
We went from IO to two-message OT, right? So that's.
But that's not the, okay, so even after you see, like, let's see, 20 or things like more recent, after this, that's a fair point. So until very recently, what we knew is that we had to assume either like cryptomania assumptions, like public encryptions and zaps and so on, or we had protocols that were based on strong forms of one-way functions and were limited to a constant number of parties.
Just to understand, the information theoretic construction is not ruled out.
Yeah, it is ruled out. We can prove that for 3 rounds you cannot do it. Yes, it's actually in a paper with Arpita and Delirium. Okay, so we'll see where it comes from. Let me talk about the first 2 applications. So let me start with multi-string NISC. So non-interactive zero knowledge, I guess that, again, we all know the concept, and this is a very useful, very wonderful concept, but one kind of drawback of this concept is that we have to put trust in this CRS, right? And if this CRS is not generated properly, then, you may lose soundness, you may lose zero knowledge, right? And the standard solution is to distribute the trust. So you have a couple of entities. You run an MPC protocol among these guys in order to generate the CRS, right? That's the standard solution. And this is typically expensive, right? Both it's in interaction, in communication, in computation. And this is especially the case when the CRS is structured, right? I mean, think about RSA parameters. This is things that actually, I think that in the real world, right, practitioners are interested in these kind of things, right? I mean, so this is a real issue. This is not just a theoretical problem. So there's at least in theory, there's a very elegant solution by Rafi and Groff. And their notion is, they define the notion of multi-string NISCs. So they want to split the trust, but in a non-interactive way. So each of these guys generate its own CRS. And now there's a protocol. The prover and the verifier see all these CRS, and we have the guarantee that as long as we have honest majority among these entities, the protocol will be secure, right? I mean, sound and zero knowledge. So that's great. And kind of miraculously, they show that you can actually realize this notion based on if you have a NISC, a standard NISC, in which the CRS is uniformly distributed and one-way functions. Okay, so this is a very cool result. The natural question is what happens when you have NISC that is not, does not use a uniform CRS? And this is, in many cases, this is the cases that we're interested in, right? I mean, like in the RSA parameters, for example. So can you kind of transform it into multi-string NISC? And what we show is that the answer is yes. So this is an analogous result to the result of Groff and Dostovsky. We can show that given a NISC over arbitrary CRS and one-way functions, you can generate a multi-string NISC. And you'll see the proof in a second. And this is a very modular and very generic proof. So we get, as a bonus, all sorts of additional features. In particular, we can maintain succinctness and things like this that are not preserved in the original proofs. Good, so let me show you the proof. Okay, so we start by generating the CRSs for standard NISC. And now our prover who holds the circuit and the witness is going to use this NPSS in order to generate this F1 up to Fn. And we're going to set the threshold in a way that will get privacy against any minority and recovery for any majority. Okay. So this guy generates all these partial assignments and the global assignment. And he's going to commit to the global assignment. And now he's going to send n proofs, right? Where the ith proof is going to be a proof with respect to the ith CRS. And the statement will be there exists a partial assignment that satisfies Fi and is consistent with the commitment. Okay, so that's the system, and the verifier is going to accept if all the proofs accept.
Consistent with a global commitment.
Yes. Okay, so let's see why this thing works. So let's start with soundness, say that this prover is cheating and maybe collaborate with few of these guys, right? I mean, there are also cheaters. Well, if we have honest majority, right? I mean, so let's say that these 3 CRSs were generated honestly, then we have soundness with respect to this thing. It means that in order to cheat, He has to find partial assignments that satisfies F1, F2, and F3. But by the recovery property, this means that you can satisfy the original thing. And actually, the way that I define things, I can actually extract this thing, so it will give me also proof of knowledge if the underlying components are okay. What about zero knowledge? So say that the verifier is corrupted, and they collaborate with, a minority of these guys. So a minority of these CRSs are bad. So all the information for these CRSs is leaked. But that's fine. It's a minority, so I leaked only a minority of these partial assignments, and the NPSS privacy property guarantees that this information is simulatable. Okay? And you see that we make so that's it, that's a proof. We make a very kind of simple use of the commitments, and if I switch to statistically hiding commitment, I'll get statistical zero knowledge, and so on. This notion is this notion is very robust.
So this is a combiner for NIZK that makes a non-black box use of the one-way function, right?
Yes. Non-black box use of the one-way function, but a black box use of the underlying proofs.
Yes, but can you comment about necessity of the one-way function?
I don't know, that's my comment.
Sorry, one more question. And what alphabet is this commitment over? How big is alphabet?
So depending on your commitment, right? I mean, if you want things to be succinct, use collision-resistant hashing, and use a Merkle tree.
The alphabet of the symbols in Y. In the previous slide, there's a Y. How big is the alphabet?
What do you mean, like each bit? I mean, this is a bit string.
Oh, it's a bit string.
Yeah.
So the T+1 threshold is for bits. It's not for field elements.
No, the T+1 threshold is for sets. So we think about the partial assignment that is defined for the Fi. It's not every set of T bits.
Okay.
Okay. So, how am I doing with the time? Okay.
10 minutes.
Great. So we can actually extend this thing in several ways, and let me show you something that at the beginning does not look very interesting, but I'll argue that this is interesting. So let's say that I'm going to relax this notion of multi-string NISC, and I'm going to allow these authorities to send a private key or a private message to the prover. Okay? So this kind of corresponds to what people call designated prover NISC, right? When the prover has a secret key that allows him to prove things. Now, it turns out that if you apply this relaxation, then you can get rid of the NISC. So you can get this notion in the multi-string model just based on one-way function. And the reason is simple, right? I mean, we can use the one-way function in a fairly simple way in order to get a designated prover NISC, okay? And then we apply the previous transformation to this standard designated prover NISC in order to lift it to the multi-string model. Okay? So we get this thing. This thing does not look very interesting in the context of NISC, maybe. But now if you think about it as an MPC, in the context of MPC, this suddenly becomes interesting. Because what we have here is actually two-round multi-verifier zero-knowledge proof. Right? I mean, think about these guys are participating in an MPC protocol, and one of them wants to prove a statement to all of them. And let's say that we're in the honest majority setting. So I can think about this protocol as a two-round protocol where these guys generate, send this thing in the first round, including plus the private messages. In the second round, this guy broadcasts the proof. And it has even additional features like external observers can also be convinced that this thing works. So this is nice. And previously, we only knew how to achieve this thing under the assumption that you have NISC. And we can also get here, again, additional features like what people call everlasting security and so on. But the most important thing is that we can actually use this thing by using a template that we had in a paper with Arpita and Eliran to apply the GMW paradigm to move from passive security to active security by paying only a single round. Okay? And this means this is exactly the key component that is missing in order to get a 3-round honest majority actively secure MPC just based on one-way functions. Okay. Good. Let me say a few words about how to construct these things. Questions? Comments? Okay. So as I promised, I'm going to define a new notion of T out of an MPC. So let me explain this notion briefly. And if we have time, I'll say a few more words about this thing. So I want MPC here that has a perfect passive correctness. Okay, so if everyone behave well, then you know that the output is right with probability 1. I want perfect passive privacy against what I call unauthorized sets, so coalitions smaller than T. Okay, that's kind of natural. But here comes the weird property. I want perfect active correctness with a board against any set of n minus t plus 1 corrupted parties. Okay, so this is a bit weird. You see that the threshold here is very different than the threshold here. And another way to kind of write the last item is to say that the adversary cannot fool an honest set of parties of size at least t. Just a second. Okay. So if you think about it, what we have here is actually an MPC that behaves like a secret sharing scheme. I mean, if you look at any set of, say, at most t parties, they know nothing, right? You have privacy. But once you have a set, a slightly larger set, they contain, in a sense, all the information, like a set of size t, they contain all the information about the output of the protocol, okay? So this is kind of a tricky notion. If you look at protocols from the literature, they don't realize this notion. I mean, think about your favorite protocol, like the BGW or something like this, or whatever you want.
Linear PCPs, they do, right? Because you just need to compute linear functions, and then you just need the honest parties to define.
So if you restrict yourself to linear function, then they do, but I don't see the linear PCP step. I mean, but let's take it offline. I mean, I don't think that, like when you do the linear PCP thing, don't you? I mean, you're going to lose the threshold, right? I mean, you're not going to have tight threshold.
Challenge that defines the linear function of the input. So honest parties, as long as the honest parties determine the proof, then it should be.
Okay, so, I don't know if this works. It will be interesting. I think maybe I will explain in a minute why it will be interesting. So this is kind of a slightly weird notion, and what we show is that you can actually construct it in the OT hybrid model. So this kind of, so in your solution, you don't use OTs, because if this is the case, then it shouldn't work. I think you can show that OTs are necessary, I think. But okay, let's continue this discussion later. So we get a construction in the OT hybrid model, which is perfect. And the construction is kind of tricky. We start by realizing the most naive version of this problem, where you have just two parties, and the threshold is either 1 or 2. So for threshold 1, this is the replication thing that I just said, right? Each party gets all the information and just compute things, right? There is no privacy, you just need correctness. And for the t equals 2 version, it turns out that the GMW protocol exactly achieves it. And in this case, indeed, you have kind of privacy, but you don't have the correctness. The correctness becomes a kind of trivial, right? There is no correctness property. So once you can do this 2 out of 2 and 1 out of 2, which kind of correspond to AND and OR, you can kind of compose them by using a formula, using this virtualization technique that was mentioned also by Vipul. And we exploit the fact that there is a polynomial size monotone formula for threshold functions, say by using sorting networks. And therefore, this is the way that we get this result. So it's kind of tricky, but it works. And finally, in order to get an NPSS from this kind of thing, we are going to use a variant of MPC in the head. And there's a minor trick on this classical work of ICOS. And it turns out that since we are working with an OT channel, we actually get this property of partial assignments that I mentioned before. So I'm not sure how much time do I have? 2 minutes. Okay, so I'm not going to talk about these details. Read the paper and see where it comes from. An interesting open question, get rid of these partial assignments, like, or prove that this is necessary. Okay, I don't know. Just to give an example of what this notion of MPC means, because I think that I'm not sure that everyone got it. So let's look at the 4 out of 5 MPC. So 3 parties know nothing. But if you look at 4 parties, they are protected against any adversary that lives here. In particular, if their inputs fix, say, the function, the residual function to 0, this adversary cannot force the output to be 1. He can abort the protocol, but he cannot change the output to 1. Okay, so this is kind of the definition that we have. As I said, existing protocols fail to achieve it, and note that this notion is kind of non-monotone with t, right? Typically, when we increase t, we get more privacy. Here, kind of, I have t and I have n minus t plus 1. So when you increase t, you get something incomparable. So it was a small miracle that we could even realize it for every t. It wasn't clear at the beginning. Good, so let me kind of summarize. So we have this new notion of information theoretic MPC with these threshold behaviors with respect to privacy and correctness. We see again that virtualization is a very powerful tool. If you don't use it, you should. We get this notion of secret sharing for MP statements, several interesting open questions, and I'll be interested to see more applications of this notion. I mentioned all these applications. And one thing that I want to say about this picture is that if you look at it from kind of far apart, you see that we started with an IT MPC, funny IT MPC, and we eventually solved this problem about a computational MPC. Right? And this kind of process, we see it in several cases in the literature. And I have to say, like, personally, we worked on this problem quite hard before we had this paper. And it wasn't easy, or at least we couldn't see a direct way to solve it, and we had to go through this abstraction in order to solve it, right? I mean, I don't know how to do this directly, to go from there to here. I mean, without this abstraction, I wouldn't even think about this notion of MPC. And the lesson that I learned goes back to Archimedes, right? I mean, if you have the right abstraction, it buys you a lot. 2 words about the follow-up work. So this work gives us the problem, like solves the problem of combining zero-knowledge proofs, but there's a harder problem, right? I mean, of NISQ amplification. So imagine you have a single PA, but with some probability, this TA kind of fails to satisfy zero knowledge, and with some probability, fails to satisfy soundness. So this is much harder. And the naive thing of using many TAs kind of and hoping that the right fraction of good TAs and bad TAs will be fine fails, because even when a TA is kind of good, the fact that this event happens already leaks information about say its coins and about the witness that he's using. So this is kind of tricky, and it turns out that what you need in order to prove that this was kind of like the general question here was studied in previous papers, and they left kind of they left open the basic question with getting an optimal result, like with optimal parameters. And it turns out that we can kind of mimic the same approach in order to solve this question, except that we need to add here some property of leakage resiliency. And again, property of leakage resiliency. And each of these errors now becomes much more complicated, but this is doable, and the paper will appear in crypto, and it's available online. Let me also mention that along the way, we also get new results about leakage resilient MPC in the standard model, like not in this funny notion. So I guess that's it.